this is, the Hong Kong Institute of Advanced Studies, Senior Fellow, Sir John Pendry's Distinguished Lecture. So we combine 2 to 1 so that he will only need to give us one illuminating lecture. So for those of you who have not Googled him, I'll just give a very brief introduction. So Professor Sir John Pendry is known for his groundbreaking materials on metamaterials. He worked at the Imperial College of London since 1981, and then he, had important administrative roles as well as Dean and Head of Physics. He is the Fellow of the Royal Society, and he has received numerous awards, including the UNESCO Niels Bohr Gold Award, the Kavli Prize, and most recently the Kyoto Prize, which is very prestigious. And his talk today is about materials with a very interesting title, so I'll let him speak to you all. Thank you for coming.
Yes. Well, thank you very much for that kind introduction. If we could have my slides up, please. Great. So my title is Materials That Move Faster Than Light. For some years, I've been interested in metamaterials, as we've been hearing a great deal about them today. They've really taken a hold over the last 20 years, I'd say. And their manner of operation is that they're structured in space. And simply by changing the structure, rather than changing the chemistry, you can actually create a whole range of properties, as we've seen in the previous talks, which have been a perfect introduction to what I have to say today. But the next logical step is to ask if you can make structures in time. And that's been sort of hanging fire for some years. We've had so much to do with the materials which are structured in space that it's taken a while to get around to the structure in time. So what I want to do today is to give you a report on, I think the amplification is a little bit high because we're getting some resonance. So turn it down a bit. That's better here. Background singing. Yeah, okay. It's when I move my head, I think. Sorry. Okay. So I've already spoken in Hong Kong about several aspects of materials that move faster than light, and today I want to bring you up to date with some of the things we're thinking about today. So it's very exploratory. I think what's made it relevant at this particular point in time is that we're actually getting some experiments which can change materials on the sort of timescale required. So just as you need to influence light by metamaterials by having structures less than the wavelength, so with structures that vary in time, you want to get down to at least the period of the radiation in order to have an interesting effect on how the radiation behaves. The talk will be in 2 parts. The first and most important bit, you might say, is asking what are the challenges for experiment and how are they getting along? And secondly, I'll look at some of the more recent theory we've been doing in London, trying to probe what interesting things these new materials can do for us. So for the experiments, very much the workhorse has been indium tin oxide. This you may all be familiar with because it's the thing which makes your computer screen both conducting and transparent. It's a material which can be very heavily doped, so it can be a metal with a very low electron density, which gives it its conducting properties, but with a plasma frequency which is below the visible, so it's transparent. and in particular, the samples you get tend to have an electron density which has a plasma resonance round about 200 terahertz, which is the near infrared, as you know. And this material, if you shine a 200 terahertz laser pulse on it, there's an epsilon near 0 point, a plasma resonance at that, close to that frequency. And this excites the electrons and changes the property. So if you then ask, well, how quickly does that alter the properties of this material? The answer comes out to be of the order of, well, depends on the experiment, but sometimes it's 40 periods, but we see recent experiments in which it's very short. Whereas we understand the response on a scale of 40 periods of the radiation, we do not understand the response on the scale of 1 period, which we see evidence for, but we don't understand. And I want to put forward a theory which may or may not explain it. So the incredibly fast response scale, which some experiments see, remain unexplained. I should mention that my collaborators are Simon from Exeter, Ricardo, who does experiments in London, Paloma, who's one of my former postdocs, now a professor in Madrid, Jaime, who's a student, and Emmanuel, who's a former student who's now in New York with Andrea Alou. So here are the experiments we're talking about, and these are some experiments which were first suggested by Bob Boyd in Rochester, and I've already mentioned part of them. So here is the sample. There's the indium tin oxide, a silica layer, and gold. So initially, when the experiments start, at the frequency of the experiments, you're at the epsilon near 0 point, and there's a what's called a Berryman resonance, which is essentially a plasma resonance, which consists of the electrons wobbling back and forwards across this indium tin oxide. And that resonance completely absorbs the radiation. So there's essentially zero reflectivity of this surface before the pump beam strikes. When the pump beam comes in, it's absorbed, and that energy goes into promoting the electrons within the conduction band. And the effect of that in conventional theory is that the effective mass differs according to where you are up in the conduction band. And they get heavier as they go up in energy. And that heavier effective mass, of course, the plasma frequency reduces if the mass of the electrons increases. And that means the resonance suddenly vanishes, and the indium tin oxide suddenly becomes transparent. Now, the significance of that experiment is that whereas most nonlinear effects in this range are very, very small, and you're talking a fraction of a percent, this effect is huge. So two things here. One is that the resonance enables a pump to dump a lot of energy into this system. Secondly, epsilon is near 0, so percentage changes of it are much greater. So a percentage of 0 is infinite, of course, but of course there's the imaginary part as well. And actually the change in reflectivity here can be, as you see from here, this is reflectivity measured as a function of time. And the increase in reflectivity is approaching 60%. And that's a phenomenally strong nonlinear effect, a fast nonlinear effect. Now, this is a measurement made with a probe which is 40 cycles wide. And so it really doesn't probe how rapid this rise time is, other than to say it's at least 40 cycles of radiation, narrow or wide, whichever you prefer to call. So that's the switch on process of the excitation of electrons. And the model people take for this is a so-called two-temperature model, because to excite electrons substantially into the conduction band requires an electron volt or so. An electron volt measured in temperature is 10,000 degrees Kelvin. That would melt the lattice. And so you have to have a two-temperature model, one for the electrons and one for the phonons. And this decay, which is slow, is a gradual dissipation of that energy from the electrons into the lattice, where it's diluted, and that decay is very slow. So we don't use that. We use this leading edge here, and that's the fast bit. But what I'll show is that in practice, that leading edge is much sharper than we thought. Okay, so just to go through the two-temperature model of the conventional theory of the reflectivity, I think it was Bob Boyd's group that originally put this forward, but other groups have worked on it and refined it. So as I've explained before, there's a plasma resonance known as the Berryman resonance, which enables the thing to be to absorb energy and also to cut off any reflectivity before you start pumping. So that's why we choose this particular frequency. And what I've said before is that what the model proposes is that what you're doing is heating the conduction electrons and promoting them within the conduction band. So you in this model, you're working with a fixed number of electrons that's given to you by the doping. The valence band does not feature in this model, and the argument for that is that this radiation has about 1 eV of photon energy, and the band gap in ITO is about 3.5 volts. So there are no direct transitions or indirect transitions or whatever possible with 1 photon being absorbed. It can only promote electrons within the conduction band. That's the only place to go with direct excitations. And then when you push the Berryman resonance away from that frequency, there's transmission and you get reflection and then slow reach. And this theory is very successful on the scale of 40 femtoseconds. For example, here's a paper by our collaborators in Exeter. The theory here was done by Simon, and they implement the two-temperature model. And here is the reflectivity data, and here is the theoretical simulation. And so you might say, what's not to like? The fit is very good, even though the experiment only has a resolution of about 40 femtoseconds, which is the width of the pump and the width of the probe as well. So the theory reproduces that very well. Well, what's not to like? Unfortunately, these criminals at Imperial College did this experiment, which completely blew out of the water the two-temperature model. And their experiment was to, or our experiment, I should say, because I did some of the theory behind this. The question was just how sharp was that rise time? So you've seen the rise time, which is measured to be at least 40 femtoseconds, because the probe, that's the width of the probe that measures it. But how narrow, how sharp really is that resonance? And the solution we sought was to go back into time to young slits. And if instead of having a single pulse incident on this system, you have two successive pump pulses and then a very broad probe instead of a narrow one. So the probe's there all the time, and then this pump comes along and goes zap, zap, and it makes two holes in time, structured in time, in the same place physically. That gives rise to some interference fringes. Let me explain. Now, you all, I'm sure, know about Young's slits experiment, which produces, so slits in real space gives fringes in reciprocal space, in K-space, and they're viewed when you view them in the far field. And the period of these fringes, it reveals, whoa, this is like using a rubber wand to point, reveals the spacing between these two slits. But there's some more information there, which is less commonly known, and that is that if these slits are very narrow, they will diffract through a large range of angles. And if they're broad, then the focus is more sharp. And so the way these fringes die away in reciprocal space reveals the shape of the slit. In fact, the profile of these fringes, A of K, in reciprocal space is the Fourier transform of the shape of the slit. So you have the structure factor, which is the separation, and the form factor, which is the shape of the slit. However, what we're interested in are things that are slits in time. So now if you have slits in time, you put in a constant frequency wave, which is the probe, which has a well-defined frequency. But now, because this slit windows it in time, you create a range of frequencies, and that range of frequencies is determined by how narrow this slit is. If it's infinitely narrow, then you spread that frequency out. It's a delta function in time space is infinite bandwidth for frequencies in reciprocal space. So this structure factor is now telling you about how sharp these slits are in time, and the period again is the spacing of the slits given by the spacing of the slits in time, and the fringes are observed in a spectrometer rather than in the far field. So you put the result coming from the probe through a spectrometer, and you see fringes in frequency. And that is a way of measuring something which is much sharper than the width of either of these objects we're considering. Here are the data. This is the experiment, the hairy one with noise on it, of course. And you can see that it's the simple part of the theory is to project this period well, let me explain what's going on here. So this is the central frequency, and this is how far down in frequency you've been shifted by the width of these slits. And as you can see, there's some fall off here, and it's the way this fall off is going to tell us how sharp the slits are. The period of these oscillations is constant, and it's dictated by the spacing. That's a very trivial thing almost. And you can see that if you decrease the spacing in time, the spacing in frequency increases. And of course, the theory reproduces that. But also the theory reproduces the fall off in frequency change. Now, by the way, you might be interested that that was reported in this paper here in Nature Physics last year. What is this theory that's I'm talking about? Well, if you make the most elementary assumption about what the slit looks like, our first guess was to assume that the slit is made infinitely quickly. So you have a step function and then a slow decay of the reflectivity. Now, the Fourier transform of a step function in frequency is 1 upon delta omega. And that's how the amplitude drops off, but the intensity would drop off as 1 upon delta omega squared. So if you multiply those data by delta omega squared, you should get a constant. So here's the theory, which is the dotted line, and here's the experiment, both multiplied by delta omega squared. And you can see that the theory, of course, is based on a step function, therefore it has constant oscillations. But if anything, the experiment is outdoing the theory and is even sharper than a step. So what this is saying is that on this time scale, on this frequency scale here, we cannot detect when these fringes are going to die off in intensity. Something is happening there which is so sharp that it is producing these very, very long range fringes. And what they reveal is that we've gone out in the measurements this far, and what that shows is that the oscillations reveal that the step is at least as fast as 1 to 10 femtoseconds, which is about 2 or 3 periods of the radiation. And that's much faster than the two temperature models predict. And the problem with the two temperature model is that it's like boiling a kettle. So you're putting heat in and gradually the electrons, and eventually they get there, all right, on a sort of time scale that the pulses. So if you had very, very sharp pulses, you could do this very quickly. But we don't have a very sharp pulse. It's 40 periods long. So it's a kettle boiling thing. So how is it possible that on those time scales, as I've shown you, the two temperature model is very, very successful. So we were both delighted and puzzled. We were doubly delighted because we really didn't expect anything from this experiment other than confirmation of the two temperature model. And it was given to 2 MSc students to do over the summer. And they did a really good job, I have to say. We did put their names on the paper. Now, here are some more data which are interesting and which the step model does not explain. So when you have a sharp slit in time, so if you window something in time, you have a spread in frequencies, and you both go to lower frequencies, but also you go to higher frequencies as well. Now, it turns out that if the windowing function is just an aperture or a pure step, which is so the reflection coefficient changes, let's say, from 0 to unity, then there is no way that you can do anything but get a symmetrical distribution about the 0. But what we have here is a measurement of, so this is the frequency here. So this is the, this is the pump frequency now, but now at the center. So this is losing energy, and this is gaining energy. So this is a blue shift, and this is a red shift. And what they do here is vary the separation of the slits. And this is the intensity. And you see fringes, so you can see the oscillations here, and also you can see the oscillations getting closer together, this slope of this line here, as you increase the separation of the fringes. But what you also see, which is not explained by our crude theory, is that there's this huge asymmetry between fringes which are red shifted and fringes which are blue shifted. And that's not explained by the two temperature theory either. So we both theories are in a quandary. They don't, one explains some of the data, the step explains more of the data, but neither accounts for this asymmetry between the red and the blue. So what to do about that? Well, it is clear that you have to somehow accommodate the two temperature theory. On some time scale, it's explaining what's going on. So you've got to allow your model to incorporate any new theory, but also to reproduce the same data that the two temperature model produces. And so this is the model which I'm proposing. I don't say it's right. I just say it explains the data we have at the moment. There may be more data that says that it's wrong, and we need more data. But I'm giving you a work in progress. So what I'm proposing is that the event, it must be localized in time because something very sharp happens at some very, very specific time. So it is localized in time. We know the data tell us it's localized in time. It may also be localized in space because it may only occur where the beam is very strongly focused. So the width of the spot is many wavelengths wide. It's hundreds of wavelengths wide. It's not one of these spots that we saw in the earlier talks where you can focus down to a wavelength. This spot isn't like that. It's very broad, but in the center, of course, it's sort of Gaussian or what have you. And maybe it's in this sort of nucleus of the illumination profile that this new event is taking place, that this event may be localized, it is localized in time, but it may also be localized in space. That's the sort of excuse for bringing a new theory on top of what we have already. So just to summarize the significance of that, reveals the first time that reflectivity is structured on a timescale 2 orders of magnitude shorter than the pump width. So we must have some catastrophic event in time and possibly in space. And we've got completely to rethink the data, the theory rather. So here's the model. Let's hurry up, I'm talking too much. Okay, it's got to capture the key process about an experiment. So we construct models that look something like reality and explain most of the significant data, but are not necessarily things that give you the last decimal point in the reflectivity or whatever. And the purpose of the model is to give us an understanding rather than a complete way of constructing the data. So with that caveat, I'm going to propose a model which I hope will capture the key processes. For example, if you are in electron physics, there's something called an Anderson model. An Anderson model of a disordered solid is a very crude one. It's just a single band model, a lattice sites type binding site, and each site is disordered. It's nothing like with precision the models, the reality of the materials in which localization is observed, but that simple model enables you to study theoretically to give you an idea of what might be going on. By the way, it has not been solved. Right, and therefore, because we're aiming for an understanding rather than precision, we should eschew all extraneous complexity. So it's what I call a bare bones model. And ideally, you want this model to be fairly easily soluble, preferably analytically, because if you're going to have to put it in a huge computer, you're then going to have to spend a lot of time understanding what the Dickens the computer is doing. So you want it to be simple enough that you can solve it. And also, it should make some further experiments that have not been made at the time, which will test whether the model is right or not. Okay, here are the challenges. So we've got to explain this catastrophic event. Some other experimental data I didn't mention is that there's a threshold for these fringes to appear, and they only appear when the pump intensity exceeds 50 gigawatts per square centimeter. And the third point we've just looked at, that the fringes have a vast asymmetry. I didn't mention it, but if you look at this scale is logarithmic. And the difference between the intensity here and the intensity there is about a factor of 20. So that's quite an asymmetry. It's not something you could ignore. Also, as well as this asymmetry, you have the fact that whatever you propose, after the experiment has been done, the itoe is intact. You don't blow holes in it. The laser intensity is such that you do not create structural damage, so you mustn't overdo it. Okay, here's a model. Some of you may have heard of something called an avalanche diode. An avalanche diode works like a normal diode up to a certain point. So in a normal diode, if you back bias it, the conductor, the electrons migrate to one electrode and the holes to another, and there's nothing to conduct until you reverse the bias and the current flows. So there's a strong electric field in the semiconductor separating the two sides of it. Now, if you increase the back bias sufficiently, there will always be a few stray electrons in there. And if the field is sufficiently strong to be accelerating those electrons so that they're traveling fast enough that they have enough energy to do an Auger process. Now, in an Auger process, one electron falls down in energy to some lower state, and at the same time, it excites from the valence band an electron up into the conduction band, leaving a hole. So although the radiation we have cannot produce a direct transition between valence and conduction lengths, there's this indirect Auger process. Because these fields are so intense, I'm proposing that you can push the stray electrons along so quickly that they in fact have enough energy by virtue of the strength of the field rather than the frequency of the field. They can do the Auger, they can kick electrons up and alter the electron density in the conduction band. So, and the other thing about the avalanche model is that it creates an avalanche because the Auger process adds another electron to the one which has done the excitation. So next time along, the next cycle of radiations, of course it's an AC thing, in the next cycle you push 2 electrons along, you get 4, 8, 16, exponential growth. It's not linear growth, not boiling a kettle, it's an explosion. Okay. And that's the mechanism for a very fast process that actually increases the electron density in the conduction band, and it does so with exponential growth in time. So we borrow from the theory of the avalanche diode to see that instead of just a DC voltage put across, the voltage, the electric field, comes from the incident radiation. It's immensely strong, 50 gigawatts per square centimeter, set fire to things. And the other thing about the avalanche diode is it just goes on avalanching. So if you take the bias off, it goes back, no damage to the diode. It's used in voltage regulation, actually. So that fulfills our requirement that you're not destroying anything when you're doing this experiment. As the electron density increases, so does the plasma frequency. Now, that's actually the opposite of what the two-temperature model does, because the two-temperature model increases the mass of the electrons, and that pushes down the plasma frequency. So that's, the two models are, in a sense, aren't compatible, and that's why I have to separate them in space. That's if my model is true. And when this happens, if the plasma frequency then rises up, then below the plasma frequency, if you're not on resonance, the material becomes reflecting. It becomes a metallic. Okay, so if you're on resonance, you're absorbing radiation. If the resonance is above your frequency, then you're reflected. Okay, so that's the mechanism for creating a sudden pulse in intensity. And then after the pulse has gone, the electrons relax in the known way, and I don't care about that because it's not fast. Okay. So here's a few very, very simple calculations. I said it was a bare bones model. So if you put on a voltage electric field E for a time t, then just applying Newton's law, this is the energy you get in time t from this electric field, and it depends on the electric field, charge of the electron, and the mass of the electron. And the assumption is that as soon as this energy is big enough that it can create an Auger process, it does. Auger processes are very fast. I used to work in electron diffraction, and electron Auger processes are very fast. They're responsible for the lifetime of low energy electrons in solids. However, we're dealing not with a constant electric field, we're dealing with a field that goes backwards and forwards because at the frequency, a very, very high frequency. So if in one half cycle, the electron does not achieve enough energy for the Auger process, then this process, there won't be an Auger process and you won't get an avalanche. And this time is given by the amount of energy you need to cross the gap. And that's the time which you have in which to create an Auger process. And that time has to be less than a half cycle of the radiation. And that gives a threshold. And but once you pass the threshold, the rate of increase of electron density, blah, 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 blah. And the important number is this one here, that you, starting from some initial electron density, you get an exponential increase because of this doubling of the electron density. So that's the model. Where are we? Okay. So the threshold, does the threshold work? Well, if you put in the known band gap of ITO, which is 3.5 volts, then it's a cutoff when the energy is below 10 to the 11th watts per square centimeter. That's about the same order of the figure which the experimentalists see of 5 times 10 to the 10th. So I'm not into decimal precision here, as I warned you, but I said that's very suggestive. I think it's the right order of magnitude. Now, what about the reflectivity? So I have to make some assumptions about how the electron density is related to reflectivity. So I take a Drude model of the permittivity of a metal, and the plasma frequency is proportional to the electron density. So there's electron density, which we saw before. The electron density, which is increasing exponentially in time. And here is the epsilon, which is also the imaginary part of it is increasing exponentially in time. And that's our hope for a really fast process. And then you use the formula for the reflectivity, a normal incidence, which is 1 minus the refractive index over 1 plus the refractive index, and you get this monster here. I excuse that because it's something very, very fast and we're in a model. It turns out that the model is rather insensitive to these parameters. It's very insensitive, for example, to the starting density of electrons because of the exponential increase. And I'll show you that really the starting density really doesn't matter very much. So let's see what the reflectivity looks like. So I assume 10 to the 11th watts near threshold, and this is the sort of electric field you get. To put in the numbers here, that gives you the half period. Excuse me. And this is what you get for the reflectivity. So what have I got here? This is time. And it's measured in units of the period of the radiation. So 2, 4, 7, well, yes, okay. And this is the reflectivity, the real part and the imaginary part. Now, two things I want to you to notice about this. One is the very, very rapid rise of the reflectivity. That's one, these notches are just one, every 2 notches, that's 1 period. So 1 notch is a half period. So the rise time it looks good. It's on the same time scale as a period of the radiation. The other important thing to know is that this model, far from just switching on the reflectivity, it actually has a jiggling phase as well, because I plot the imaginary part, and you can see that starting from a phase of 0, you go through a phase of pi, or is it minus pi, I don't know, and then back to 0 again. So there's a whole sort of cycling of the phase, and it's this that's going to be responsible for that asymmetry which is seen between red and blue shifts. Now, first, in sensitivity to the background electron density. So what I've plotted here is the reflectivity, the modulus of the reflectivity as a function of time. And I plotted it for 2 very different electron densities. This is, they differ by an order of magnitude. So the higher density, the exponent kicks in at earlier times, but even if you start at a much lower density, you only have to wait a few periods before that also kicks in. And by the way, they have the same shape. So if I translate this red curve back in time, it precisely overlaps the blue curve. So electron density only predicts where in this cycle, in this width of the pulse, whereabouts you're going to get this glitch in time. And that's one of the things I'd like experimentalists to look at. Where does this kick, which is giving the fringes, come in the envelope of the pump? Okay, so that's one thing. Now, this is how the reflectivity changes with pump power. And I'm varying the pump power now by 2 orders of magnitude. I start off with how much? I start off with 10 to the 13th pump power, and then I wind it down to the threshold, which is around 10 to the 11th here. So as you'd expect, higher pump power, you pump faster, the kick comes in earlier, and it's sharper. If you pump with 100 times lower power, the kick comes in, it comes in later. But given that it's exponential rise, given that it's an exponential rise, it's still going up pretty fast. Of course, those slides I showed you before were calculated for this pump power here. All you get for higher pump power is something even less than 1 cycle. Have I got everything there? Yes, okay. Oh, now, sorry about this, but I love analysis. I'm sure most of you don't, but anyway, if I'm going to tell you anyway. This integral here, which we have to do, which is the Fourier transform of the time dependence of the reflectivity. Remember I said that the way the fringes died out with the Fourier transform of the window. This is a window, and I'm taking the Fourier transform. Now this guy here has some analytic structure. It's got a square root, so the branch cuts. And the branch cut is here. Now it turns out that when the frequency is negative, you can close the contour in the lower half plane. Did I get that right? Anyway, and if you do that, you catch the branch cut. And that's where all the power is coming from. There's also a residual bit here, which if you're into contours and so on, you can see how I arrived at that. So the contribution is this negative bit here and this bit here. So this gives negative frequencies and this guy gives positive frequencies. But if the frequency is positive, then I have to close the branch, the contour in the upper half plane, and I do not catch the branch point. And you're only left with this guy here. So positive frequencies, this is the only contribution, and this is much weaker than that. And that explains the asymmetry, if you like a mathematical explanation. So mathematically, it's quite neat, I think. So here's the asymmetry. Red shift in red, blue shift in blue. So here is the reflectivity, and for some reason I've only shown the imaginary part here. I don't know why, but this is the reflectivity for a positive, for a red shift. Yes, for a red shift, and you can see that the reflectivity change is very sharp. As the shift, this is a shift in frequency, by the way. I've been very careless about noting things. And if you then look at the fringe visibility, this is now, it makes more sense. This is a shift in frequency as a fraction of the pump frequency. So this is a shift to 20% of the pump frequency and the probe frequency, which is more or less the same. And you can see that the scale here is much, much larger than the scale for the red shift. So this, sorry, the blue shift. So this is a red shift, which is big, and this is a blue shift, which is small in intensity. And that's for a very, very low electron density, which is lower than the specimen that the experiment was on, actually. But it does illustrate the very dramatic difference in fringe visibility. If you bung up the density to what they have in the experiment, this is the experiment in the samples you get typically in your cell phone, you find that the asymmetry is less, but it's still substantial. So how did we do? How am I doing, by the way, Ding Ping? How much? No, right. Freedom. Okay, so how do we do? Yeah, you can predict the visibility of the fringes going way out, no problem at all. So that we do. There's a threshold predicted by the theory, which is given by the threshold for Auger processes in 1/2 cycle. There's the asymmetry of the fringes between positive and negative frequency shifts, red and blue shifts, and that's predicted by this curious analytic structure whereby there's a huge jiggle in the phase, and that creates the asymmetry in the way we indicated. And because we know from avalanche diodes that these avalanche processes are not necessarily destructive. If you push them too far, they are, of course. You can easily set fire to a sample with a very intense beam. Now I want to move on to the theory, and unfortunately I've not left very much space for our very brilliant theory. And one of the things which we're looking at the moment is how putting a sample into motion. So we're not talking about real motion here. This is like a modulation of the refractive index that appears to move in time. And you're not moving this. It's a bit like a wave on the ocean. So a wave goes across the ocean, and you're not actually transporting the ocean with a wave, right? And so here, when you're modulating something in time, you're not actually pushing the thing. And that means that you can move the modulation as fast as you want, because it's a phase velocity rather than a group velocity, which is restricted. If you move the material, you're restricted to be less than the speed of light with which it moves. So what is this density of states things? Well, I'm old enough to remember, in fact, I wrote the News and Views piece on it. Eli, in fact, it's what got me into structured materials in the first place. Eli Lubonovitz suggested that you could actually make an analogy between semiconductors for electrons and insulators for light. So you're familiar with the concept that in a semiconductor, you can have a band gap where there's zero density of states for electrons, and that makes for an insulator or a semiconductor. And he pointed out it was possible to make a structure in a material, a periodic structure, which has a band gap for photons within which there's no density of states. And that means if you have an excited atom and with a transition frequency lying in that band gap, if that atom is in one of these cavities, a photonic crystal, it can't let go of that energy. So I like, when I'm talking to children, which I'm not today, obviously, but I like to say, well, if you were inside and you tried to strike a match, it wouldn't light. That was for a lecture I gave in India many years ago. So what is the density of states in systems which change with time? You can manipulate it with structure in space, but can you manipulate the density of states with motion? And the answer is yes, otherwise I wouldn't be talking to you. So let me take a very, very simple model. This is a model which has been much used for studying time-dependent systems. And just as when you look at structured solids, you look at Bragg gratings and think of Bragg scattering. So we think of a Bragg grating in time. This is a refractive index. This is modulated so that it moves with some velocity, c grating velocity, and it's just a single cosinusoidal modulation. And often, for simplicity, we assume that these structures are impedance matched, so you don't have any complications from back reflection. That's interesting, but it's a complication I'm not interested in this time. So I'm assuming impedance matching, no back reflection. Now you can do quite easily, which Paloma, when she was working with me some years ago, did, and find what are the effective parameters of that. What's the effective epsilon mu, if you like. So here they are. So along the direction of propagation of the grating, so along the x direction, there's no change in epsilon. But perpendicular, you do get a change, and it's a very interesting form. So it's proportional to the square of the modulation of the grating, proportional to the square of the speed divided by this denominator, which is very interesting because this correction diverges when the grating is traveling as fast as light, which it can do. And also there's this factor here, which because the grating is moving in one direction, you break time symmetry. And this is the breaking of time symmetry. And that couples the electric and magnetic fields and gives you the asymmetry due to sort of apparent magnetism, if you like. And that gives you this dispersion relationship here. So perhaps easiest to see is the dispersion surface. So here's a dispersion surface measured for kx along the direction of motion of the grating and perpendicular to the direction of motion, excuse me, of the grating. And what you see is that it's highly asymmetrical. So you increase the wave vector of the system dramatically in the direction of motion of the grating, and you have hardly any effect whatsoever in the back direction. And so this is, we wrote a paper, let me see whether I show that paper here. No, I don't. So what this is an example of is Fresnel drag. You may have heard of Fresnel drag. Fresnel said that if light propagates in a moving liquid such as water, and this is a really moving liquid, okay, that Fresnel was talking about, then its velocity should be dragged along in the direction of the water. Not at the same speed as the water. It's a very complicated formula, and his derivation was wrong, but his answer was correct. The correct derivation had to wait for special relativity. And Fresnel drag is one of the foundations of special relativity. And our question we're answering here was, could a medium which had not real motion of the material, but apparent motion, so this grating is apparently moving, the material isn't moving, could that do Fresnel drag? And this shows that the answer is, the answer is yes. You get different velocities. So paradoxically, you can see that the light now is moving more slowly in the direction of the grating rather than faster. So it's sort of anti-Fresnel drag. Anyway, what you can also do using that formula is to calculate the density of states, which changes, and I'll show you that. Well, I can show you that in this slide here. So the density of states is inversely proportional to the slope of this line. So the density of states is dk by d omega, which is 1 over d omega by dk. So the flatter this line, the higher the density of states in frequency. And so you can see that you're increasing the density of states with this virtual motion. But much more dramatic is the increase of the local density of states. So not only is there an integrated density of states as a whole, but the density of states can vary from one part of the material to another. And what I've calculated here is that if you take a grating which is very, very weakly modulated, this is 2.5% modulation, but is traveling very close to the speed of light, then the local density of states gets compressed near certain points in the grating. And this is the intensity of the density of states. If I actually plot the waveform of the modes that are responsible for that, they have their phase very intensely compressed here. So not only does motion change the density of states, it has a very dramatic effect on the local density of states. What is the consequence of that? Well, here is the local density of states in a solid. Here is a mode in which an excited atom might be emitting. Here is the mode of frequency omega, same frequency, into which your atom now has no choice but to emit if it wants to. And you can see that the phase is stretched here and compressed here. And so there'll be a very different transition probability in this moving medium than there is for a stationary medium. So local density of states is changed very dramatically. Now, you might think, since you're not actually moving the material, that just to set this modulation in motion might not cost anything energy-wise, but it does. And it does because you change the density of states. So I'm going to ask, what is the difference between the energy of a state which is stationary and one which is moving? I think classical electromagnetism, there is no reason why this moving profile or refractive index should cost you anything. But if you look at quantum electrodynamics, the answer is yes. And the reason for that is that the density of states, each mode is populated by an energy of a half h bar omega, a 0 point energy. So you do, if you change the density of states, you do alter the amount of energy in there. So here's the calculation. Very, very simple. This is the total energy of the system. You're integrating a half h bar omega up to some cutoff frequency, which is when the material stops responding to light, as it will at some cutoff frequency, which I take to be in the near UV. And here's the density of states. And that's given by dk by d omega, and then integrated over all the sphere and so on and so forth. Now, when you do all that, this is the formula you get. And this is the important bit here, that this is, the black is what you get without motion, and this is the additional term due to motion. And it's proportional to, in the slow speed limit, the square of the grating velocity. So let me put some numbers to this. What I should, most important thing, that if you have an energy which is proportional to the square of the velocity, then that's like a massive object being accelerated. So you can actually attribute a mass to this moving stuff. What is that mass? So here's a calculation, and you can phrase it in terms of the energy which the 0 point energy which the system has when it's not in motion, and that is 30,000 joules per square cubic meter. And the mass of the grating is really, really, really tiny. It's this, but you have to remember that you're going to move this guy at something like the speed of light. So even if it's not very massive, to accelerate a fly to the speed of light would certainly take a lot of energy. So even though this isn't very massive, it can be significant when this number comes close to the speed of light. It can be of this order here. So to my conclusions, if you think back to the beginning of my talk, we have a current generation of experiments that construct materials on the time scale of one optical cycle. Our theoretical understanding is not well developed. I've proposed a model. The model has some predictions for experiments which are yet to be done, and it may be wrong, but it does seem to explain the known data. Now, these time crystals, although they lack time symmetry, they are PT symmetric, and so you can recover a density of states and all that sort of thing, and you can calculate its energy and its mass. And it's going to substantially change the lifetimes of excited atomic states inside these time crystals. It may even, and this is work in process, affect the lifetimes of atoms which are outside the time crystal. That's an interesting thought, which we're pondering. And you can ascribe an effective mass. It's not, you can't move this, set this thing in motion for free. There's an energy cost which is associated with the motion. And with those thoughts, I thank you for your attention, and I'm